Cepheids by Dan Alsbach, Stefano Mainella, Megan Poremba, and Julie Latanzio. So part one of this project is characterizing delta Cephei. A Cepheid variable star is a star from the main sequence that has evolved off into the instability strip. The instability strip is a narrow vertical strip on the HR diagram that contains pulsating variable stars. These stars vary in their luminosity due to changes in their temperature and diameter. These changes are predictable and useful to astronomers because the period is directly related to the star's luminosity, which allows an estimation in their distance from Earth. These stars were first characterized by Henrietta Swan Leavitt in 1908. Leavitt worked at the Harvard College Observatory under Edward Pickering as a computer. Women were not allowed to be astronomers at the time, so instead there was a group of women working at Harvard as computers. Leavitt looked at the spectrum plates of stars in order to classify them according to Annie Jump Cannon's OBAFGKM classification system. This work led her to discover the period luminosity relation of Cepheid variable stars. These stars act as standard candles because their luminosity is known, so we can find their distance using their measured flux. Her work on Cepheids was the first building block of the distance ladder that helped measure the Hubble constant. The Hubble telescope is sensitive enough to distinguish classical Cepheids up to 15 million parsecs away from Earth. Oops. There's James texting me. Okay. Here is a period luminosity relation of a Cepheid variable star that was originally discovered by Henrietta Swan Leavitt. And the equation for the magnitude is m equals negative 2.76 times the log of the temperature minus 3.16. So this is a plot of the light curve from delta Cephei. The first Julian date we have over here is 40,030. And, oh, I'm sorry. The first date we have is 40,432. And the last date we have over here is around 40,439. The range of our observation was 10 days, but it appears that the period is around 7. But this is just a guess. This isn't actually our precise period. This is kind of just a visual estimate. And the magnitude during this ranges from 3.6 to 4.3. So this is a plot of the phase diagram for a period of 5.365. We were able to measure the period better by shrinking the x limits on this until we could only see one period, which is the sine curve right here. Then we used the function phase step in Python to find the period with precision to the thousandths. Excuse me. And we can tell the period because we see a coherent magnitude variation as the phase varies from 0 to 1. Okay, so we can predict the magnitude of the Cepheid using the amplitude from the phase diagram from the previous slide and the period that we measured, which was around 5.3, I believe. Yeah, 5.3. So then we can find the luminosity of delta Cephei using the period luminosity relation, which is this equation right here. And we get the log of the luminosity to be 3.31. And then we can also find the magnitude of delta Cephei using the period magnitude relation, which is this equation. And we can get the magnitude to be minus 3.47. And then we can use the distance modulus to find the distance to delta Cephei. And using that, we get the distance to be 300 parsecs plus or minus 50. And the known distance to delta Cephei is 272. So even though our uncertainty is pretty large, we are within, the accepted value is within the uncertainty, so that is good. So thinking, like opening up this idea to other stars, if you were to imagine a variable star whose period was like super short, say like 2 hours, if you could only observe its brightness once a night at the same time every night, this is what a plot of the observations would look like, where the blue dots are your actual observations and the gray lines are the uh, variations in magnitude over time. Um, so if you were to measure a star like this once every 24 hours and it only has a 2 hour period, you can't tell, there's no distinguishable pattern, and you can't tell what the period is because to you, you can't fit this curved line. It would just look like a flat line. So the smallest period a variable star that's observed only once a day can have is 0.7 days. Um, if you have a period of 0.7 days and you can only measure it every 24 hours, you can still get a discernible pattern because the dots will not all be in a straight line. But if it's any smaller, then there's no regular variation and you can't determine the period. So the second part to this project was characterizing M100 and measuring the periods of some Cepheids in that galaxy. So M100 is from the Messier catalog, and it's a spiral galaxy in the Virgo cluster, our favorite cluster. In order to measure the periods of 5 Cepheids in M100, we're going to be using a similar method to the method that we were using to measure the period of Delta Cephei. So here we have the plots of our observation dates and magnitudes for 5 different Cepheids in M100. So here we have Cepheid 9 and Cepheid 53, 50, 31, and 55 down here. So we used folding to determine the phase value of each measured point, and we graphed the phase value with apparent magnitude to reveal the light curve. And that's this. We projected the phase to 2, so this is 2 phases, not just one cycle. So using Python, we're able to construct the plots of 5 different Cepheids. The phase diagrams give you the period, excuse me, and multiple points occupy the same curve within the period. There's some error in guess and checking this process with the phases. So from the phase diagrams from folding, we were able to find the period, which allowed us to find the absolute magnitude. So applying the distance modulus like we did in Delta Cephei, we were able to find the distances to each of these, all the variable stars that we were looking at in M100. And they're all around 10 to the 7 parsecs away, which is good. If they weren't the same magnitude, then they probably wouldn't be in the same area in space. But they're all the same magnitude and they're pretty close. They vary from like 3.6 times 10 to the 7 is the minimum, and then 6 times 10 to the 7 is the maximum. So one correction we didn't take into account is reddening. This is when dust absorbs some of the blue light of distant objects, and that can reduce the BV magnitude, and therefore it'll affect the distance that we can calculate. We can compensate for reddening by doing some color correction. So that's kind of the next step that we would want to do with this project. And here are our sources.